Back, everyone. We are going to go ahead and pick up with a discussion of IPv4 services, really, addressing services, because there are definitely some key services in the IPv4 suite of protocols that we want to make sure we master from a design perspective. We mentioned this one earlier, network address translation. We know this is a Band-Aid, a key part of the Band-Aid that is that private IP address space. We can have and we can use private IP address space. We can use it like crazy in our internal networks, just duplicating addresses from one site to the next site all we want. Yeah. We know how often the 10.x address space is used, right? We still know how often that is utilized, and we can duplicate it again and again and again, right? We can duplicate that address space again and again and again in these private environments, and that works out just fine because of network address translation. So network address translation, a huge Band-Aid for the address shortage issues. Let's go ahead and talk about some NAT terminology that we need to be familiar with. In network address translation, we consider an address either global or local. So we consider an address global or local. Global is how the address is seen on our outside network, and local is how an address is seen on the inside network. All right, so right away with NAT, we want to identify a network as inside, and this is actually something you do in the configuration too, by the way. You identify the inside and the outside. And then we have this terminology of either local or global that goes along with that. So imagine a router here. Let's say it's router 6. And we identify an inside address. Let's say it's FA00 or inside interface. And inside here we have on this link, we have the 10.0.0.1 address, let's say. Okay? As this address is seen on the inside, we refer to it as local. Now, when this address goes out on the outside network, let's say this is serial 00, when it goes out on the outside network, it has to be translated into some public address. Maybe it gets translated into 54, and I apologize if this is part of your address space, just making this up. But let's say it gets translated into 54.1.1.1. This is how it's seen on the outside network, and we refer to this as the global address. So the two terms, global and local. Local, as the address is seen on the inside network. Global, as it is seen on the outside network. Port address translation. Before we talk about port address translation, let's continue this discussion of these global and local terms. So once we mastered the concept of global and local, which is very, very easy, we know global is how the address is seen on the outside. Local is seen as the address as it's seen on the inside. We then can identify what's called the inside local and the inside global address. The inside local is that 10.x address we just saw that's assigned to the host inside the network. And then the inside global is the public address that we translate that inside host into. All right, so the inside local, the address on the actual workstation, the inside global, the address that we translate it into for use on the public internet. By the way, these same terms work on the outside. There's an outside local address, and this is the address of an outside host as it appears on the inside network. And then there's the outside global address. This is the address of the host as it appears on the outside network. So if we go back and we look at this scenario, we translate this inside local address, into an inside global address for communications on the outside world. Pretty cool, huh? Now, there might be some device out here on the outside, some World Wide Web server, let's say. Okay, so there's a World Wide Web server out there. My W's look a little funny, don't they? Okay, so this outside device, it has an IP address, right? And as other devices on the outside see it, that's called the outside global address. And as inside devices would see that web server, that's called the inside global address. No. It's called the outside global address. I'm sorry, the outside local address. The terms are very confusing. So outside global is how everybody on the outside sees it. Outside local is how people on the inside of our network would see it. Okay? So local, remember, refers to inside our network. So outside local, it's how people inside our network would view that outside server. Definitely takes some practice, some memorization to get used to these terms. Now, we said that network address translation can be a band-aid for the IP address shortage. The real band-aid nature of this, why it really functions as a band-aid, is actually not just NAT. Why it's really a band-aid is port address translation, PAT. PAT allows us to take a single inside global address and translate many different inside local addresses to that one address. This is really where we get into the band-aid for the address shortage. Thanks to port address translation, we can have a whole bunch of inside local workstation addresses, and they can all be what's called overloaded or port address translated into just one real public IP address for communications on the internetwork. Another great capability is the capability of variable length subnet masking with IPv4. Variable length subnet masking also helps with address shortages. It allows us to really optimize our IP addressing design. This is because we have the ability to just assign the appropriate number of addresses that we need for certain size subnetworks. In order for you to design a variable length subnet masking design, you need to make sure that your routing protocol supports this capability. The good news is, though, most of them do, like OSPF, okay, EIGRP. These very scalable modern routing protocols, yeah, they're going to absolutely have no problem. RIP does, as long as you make sure you're running RIP version 2. Okay, so we got to be running version 2 of RIP in order to take advantage of this variable length subnet masking. Something else that we love about variable length subnet masking is that it promotes the use of route summarization. With route summarization, we have the ability to, we talked about this before in the course, we have the ability to make routing tables smaller, but we also have the ability to make our convergence domains smaller. less devices out there need to know of a network update when we work on these smaller convergence domains. What you do when you variable length subnet mask is you take unused subnets. You take subnets that you have not used from your address space and you further subnet them as needed. So as an example, we can start with the major network of 172.16/16, and maybe we need 2 large subnets off of our London router. So we go ahead and we use a /24-bit mask to create these 2 subnets. Look at this. We've got 172.16.1 and we've got 172.16.2/24. You know from the earlier design calculation we did that each of these areas can support 254 hosts, right? 254 hosts. Great, in each of those segments. So we need 2 large subnets off of those routers. So the /24 does great. It accommodates 254 hosts in each of those sections. Now we have taken our unused subnets, one of our unused subnets, that's the 172.16.3, and notice we have further subnetted it with a /27 mask over on the Spain router. Over on the Spain router, we don't need segments that are that big, so we further subnet it using the /27 mask. Each of those areas can support, of course, fewer hosts, but that's perfect. We don't need that many in those areas. Then we take one of those unused subnets. We hadn't used the 172.16.3.132 subnet, and we further subnet it, utilizing a /30 mask to accommodate the point-to-point network link that's between the 2 areas. So you see here with variable length subnet masking how we are doing a wonderful, wonderful, efficient use of our IP address space by taking unused subnets and further slicing them up so that they are designed perfectly for the areas they need to accommodate. Like we said, this promotes address summarization. Notice in this Spain router, we have the /27 at use here. So we've got 172.16.3.32, 172.16.3.64, 172.16.3.96. And we might want to have the Spain router go ahead and summarize these addresses when it advertises them to the London router. When we summarize, all we do is we go ahead and mask off the bits that are in common. If you look at this summarization example, you can see clearly that the first 8 bits are in common here. The first 8 bits are in common in all of these subnets. But then we have variation here in the 3rd octet. So all we do is we take that 3rd octet, each of those 3rd octet values, and we convert them into binary, and you figure out where all the bits are in common. We can see that all of the first bits are in common, all the second bits are in common, all of the 3rd bits are in common, all of the 4th, all of the 5th, up, and then we have variation. Notice there is variation in these last 3 bits. So the proper summary is we pull it back by 3 bits. So we pull it back from a /24 to a /21 in order to do the summarization. Isn't it interesting? When we subnet, we move the subnet mask to the right. When we aggregate or summarize, also called supernetting, we move the subnet mask to the left. Yeah, so that's the difference between our subnetting and our supernetting. Supernet, dun da da. Another service that we need to be aware of course, when it comes to our v4 addressing world is DHCP. This is a hugely popular method of giving devices out there their IP address information. Here's what happens. A DHCP comes up on a segment, a DHCP client, a machine that we have configured for DHCP. It comes up on the network and it sends out a broadcast to all of the systems on the network. And this broadcast is what's called a DHCP discover message. The DHCP discover message says to all of the machines on the segment, help! I need a DHCP information. I need a DHCP server to give me my TCP IP address information. Notice it is a broadcast. The DHCP server or servers will hear that and they'll say, hey, calm down. Here's an offer. Here's an offer for DHCP information. The client will select the first offer it receives. Maybe it got multiple offers. It will select the first one it receives that's appropriate, and it will say, okay, I'd like to send you a request for that info. And then the server will respond with an acknowledgement. Other DHCP machines that have made offers can now withdraw their offers, by the way. So this four-way handshake of a discover, an offer, a request, and an acknowledgement, while it's a bit cumbersome, it does accommodate for multiple DHCP servers out there to respond to these clients that desperately need configuration information. Finally, the last service that we want to discuss in this section is DNS. Oh boy, is this important. This allows us to find machines by their friendly name. Maybe that name is a fully qualified domain name, like in the case of www.ine.com, everybody's favorite website. Yeah, maybe that's a fully qualified domain name. And DNS is the service that's responsible for converting that to an IP address. Because we know the system needs to communicate with that server utilizing its IP address. And then, by the way, we know there's ARP process, which is used to resolve that to a MAC address. So DNS gets us started with our name resolution, and it's going to take the pretty name and resolve it for us into an IP address. DNS isn't just one server, but it's a nice hierarchy of different servers located all over maybe our corporation and the internet itself. Because it's this giant system of servers all working together, it is extremely reliable and fault tolerant. But keep this in mind. Because it is this complex system of all of these different servers, it is going to be something that takes a lot of convergence time. If you get a new domain name, for instance, you set up a new domain name, it can take 24 to 48 hours before that information properly proliferates through all of the internet DNS systems. So we love that it's fault tolerant. We love that it's built of this complex system of servers, but that does slow things down for us a bit. By the way, DNS utilizes both the user datagram protocol and the transmission control protocol, but the good news is it's the same port number for each. So we just got to memorize the number 53 is the port number for DNS, both UDP port 53 and transmission control protocol port 53. So some key technologies we examined here, things like NAT and PAT, and variable length subnet masking, and of course our DHCP and DNS services that are critical in modern TCP/IP version 4 networks. Here's a question for you. What's the name of the internal address that is used by your internal devices to access the public internet? You know what? Let's go ahead and review those 4 different terms. I find that students have a big struggle with this, so it would serve us well to review those four NAT terms. We've got a router. Let's say it's R6. It's going to be doing network address translation. One of the first things we do is we think about there being an inside half of this router. We think of there being an outside half of the router. What you want to do is you want to draw an inside host, and then on the outside you can draw like an outside World Wide Web server. We go ahead and we apply to the device on the inside one of these crazy inside only addresses like 10.10.10.1. This is called the inside local address. It's an address as we see it on the inside. It is local because it's on the inside, right? Inside local. The address we actually set up on that internal machine for communications on the internal network. Now, we are going to translate that on R6 into a public IP that can be used out on the public internet. Maybe that's 54.1.1.1. This is called the inside global address. What we translate that inside local into for communications on the global internet is called the inside global. Now, the two that tend to be tricky. This World Wide Web server, it has an outside global address. And this is, let's say it's, 32.1.1.1. This is the address as it exists on the outside, and as other people on the outside will see the address of this World Wide Web server. How people on the inside see that address is called the outside local address. And that makes sense now, doesn't it? Local, we know, is our inside people, how they see that address. Maybe we translate that address and maybe it's not the same as the outside global address. But oftentimes, for the inside devices, it will be the exact same. So it could be that it's also 32.1.1.1. But notice if we were to translate it going into the inside, it might not match the actual outside global address. So a little review of those terms for you. I find they tend to drive our students mad as our students are studying network address translation and they're trying to get that sorted out. By the way, I just thought of one more concept here I want to teach you about network address translation. On R6, you can set up R6 as your network address translator, and you can set it up to work dynamically. So we can set up dynamic NAT, or we can set up static NAT, or we can use a combination of the two approaches. What are the differences? Well, with static network address translation, you go in and you manually set up what is going to be the translation. So you say like, I want 10.10.10.1 to be translated into this exact address. Or you can set up dynamic NAT where you might say, I want this big pool of addresses here to be translated to this big pool of addresses there. And you let the router go ahead and dynamically handle translations. As I said, both static and dynamic NAT approaches can be combined on a router, one being used where it's appropriate and the other technology being used where it's appropriate. All right, well, what's next up in our course? Well, get ready, get excited. We're going to go ahead and look at the future of TCP/IP next. We'll go ahead and do one of two lessons on IP version 6. Some of the coolest, most exciting information in the CCDA course.